Hello everyone, my name is Kazi Hassan Ibn Arif. I'm a second year PhD student at Virginia Tech. Today I'm excited to present our work, HiRED, Attention Guided Token Dropping for Efficient Inference of High Resolution Vision Language Models. By now, most of us have used vision language model based services like ChatGPT, where we can give the model an image along with a prompt and the model generates a text-based response. A typical vision language model pipeline has three components: a vision transformer, a projection layer, and a large language model. First, the input image is downsampled into a smaller version that fits into the vision transformer's input dimension. Next, the VIT processes the input image into visual features, and a lightweight projection layer converts it into visual tokens. Finally, the visual tokens combined with text token from the prompt are fed into the large language model to generate the response. In this downsampling process of VLM, the visual details of the input image can be lost, which may impact the model's accuracy. To address the problem of losing visual details, many high-resolution VLMs crop the input image into multiple partitions, in addition to downsampling the entire image. We refer the downsampled version as full image and the cropped partitions as subimages. All these image partitions together are processed to the VLM layers as usual. This encoding strategy greatly improves the model's accuracy by preserving visual detail with additional subimages. However, this significantly increases the number of visual tokens too. This excessive number of visual tokens, while improving the accuracy, creates challenges during inference, especially with limited computational resources. The increased token count in the LLM input leads to higher GPU memory usage, as the context of many tokens must be stored into the KV cache. Additionally, since large language models primarily consist of transformer layers with quadratic complexity relative to the number of tokens n, more tokens results in slower generation throughput and increased response latency. One solution to this issue is to exploit the sparse nature of visual tokens as seen in the attention visualization of tokens in the LLM. As we see in the attention map, majority of the tokens are visual tokens compared to the text token. And the cumulative distribution of visual attention reveals that only a small subset of visual tokens receive the majority of the attention. As the figure shows, 20% of the token holds 60% of the attention and 40% holds 80% of the attention. This suggests that dropping tokens could effectively address the problem. Designing a token dropping mechanism for vision language model is challenging. First, determining the stage of token dropping is critical. Dropping can be implemented either within the LLM layer or before the LLM stage, which we call early dropping. For token dropping into the intermediate layer, we still need to process the large amount of tokens in the first few layers, which increases the computation and memory usage. On the other hand, early dropping, which is removing tokens before sending them to the LLM, is more beneficial in terms of computation and memory efficiency. While early dropping is a better option, designing such a scheme for high-resolution VLMs remains challenging. Specifically, the challenge is to design a token dropping that effectively drops token across full and subimages. Additionally, designing a mechanism for devices with limited computational capability can ensure its broader adaptability. Since the number of tokens directly impacts the computational resource and the GPU memory usage during the VLM inference, a token dropping strategy that operates under a fixed token budget enable efficient inference on resource-constrained devices. And finally, besides operating within a token budget, ensuring a wide adaptability also requires a design capable of supporting a wide range of tasks, such as document understanding, visual question answering, and chart analysis. Overall, the main challenge in a token dropping strategy is the trade-off between accuracy and efficiency. While reducing more tokens by dropping them can improve efficiency, without an intelligent token dropping method, it can significantly harm the model's accuracy. In this work, we address these challenges with our method called high resolution early dropping, or HiRED in short. Compared to the previous works, HiRED is the first to provide a comprehensive solution to tackle all these four challenges we mentioned earlier. Moreover, our method is plug and play, and it doesn't require any additional architectural change or training. Our design consists of two key phases: token budget allocation and visual token dropping. In the first phase, the method considers a user-defined token budget and distributes that among the input images. In the second phase, based on the allocated budget, the method drops less important visual tokens and sends the remaining to the large language model. Our two-phase solution is based on two key insights that we observe in class attention in Vision Transformer. By design, in a typical Vision Transformer, an image is divided into some patches, and an additional class token is added before processing them together in the VIT layers. The attention score of patches with the class token is a common way to understand their importance at any stage in VIT. We observe that the class attention in early layers has a unique characteristic. It highlights the visual content of an image while darkening the less important background areas. In contrast, class attention in the final layer focuses more on the background tokens that aggregate features from other patches. As a result, these tokens has more informative tokens, despite most of them come from the background areas. Based on these two insights, we designed the phase 1 and phase 2 of our proposed method, which we explain in the next slide. In the first phase, we allocate a user-defined token budget, say 100 in this example. The budget for the full image is allocated using a multiplier parameter, which we explored through experiments in our paper. The remaining budget is allocated to sub-images. For instance, if 50 tokens are allocated to the full image, the remaining 50 tokens will be allocated to the sub-images. As shown in the previous slide, the class attention from the top VIT layers highlight the visual content. Using this attention map, we calculate the ratio of highlighted region that corresponds to the 4 sub-images. And finally, we use this ratio to distribute the remaining budget among the sub-images. Once the budget is allocated for the full and sub-images, the next phase is about dropping visual tokens within the allocated budget. As shown earlier, the class attention in the final VIT layers highlights the most informative tokens. To ensure that the LLM receives tokens carrying the most information, we select top tokens from each image based on their importance under the allocated budget. The remaining tokens are dropped and only the selected tokens are passed to the next layer. In a token dropping method like ours, there is a trade-off between using more tokens for higher accuracy and dropping more tokens for greater efficiency. That's why we evaluated both the accuracy and efficiency. We use 8 model benchmarks across different categories to evaluate accuracy under different token budget. And efficiency of our method is evaluated based on throughput, latency, and GPU memory. We evaluated HiRED's accuracy on Lava Next, which is a very popular high-resolution VLM. Under different token budget, we compared it against the full execution of the model, which is 100% token budget, and naive spatial token dropping approach, and PruMerge and PruMerge Plus, which which are early dropping approach like ours. In all cases, HiRED achieves higher accuracy using fewer tokens. For example, ProMerge Plus, which uses 55% of tokens on average, showed lower accuracy across almost all tasks compared to HiRED's fixed 20% token budget. Please refer our paper for additional results on larger model and low resolution models. While token dropping generally improves efficiency, a poorly implemented approach can introduce overhead. However, our design is lightweight and delivers significant efficiency gain. For instance, with a batch size of 1 and a 20% token budget, our method achieves 4.7 times speed up in throughput, 78% reduction in latency, and 14% reduction in GPU memory. At higher batch size, these benefits are even greater, especially for memory saving. For example, when the batch size is 4 on a 24 GB GPU, our method prevents out of memory error by significantly reducing the GPU memory usage. This concludes my presentation for today. To summarize, early dropping of visual tokens using class attention of VIT offers a better accuracy versus efficiency trade-off for high-resolution vision language model inference. Thank you for listening.